Okay? And chapter 3 is more important. Anyway, we went over a few important stuff, like this and that. I'll just briefly just fly by. And then we talked about two different methods to determine N and K in our Daejeon term. The one was integration method, integral method, and the other one was differentiation method. And basically those two have very similar approach, but they are different. And I also talked about the least squares method, so that we can calculate A and B, in other words, intercept and slope for our regression line. Okay? And then, so I think we did it up to here. And I also remember that I asked you to use second order polynomial and come up with A and B and C. So I believe everybody did it. So, and that's your homework. It was actually. All right. And then we often also, where do we have whiteboard? Okay. And now let's say we have T and X and Y, and we had a whole bunch of experimental data, and now we try to find a good solution, equation that can be good to represent those data. And this must be A, this must be B. And also, right here, B is this. In this case, this is line, right? Line. First order equation. First order equation. Right? And second order equation, or let's say a poly means is more than one. A single is one, and polynomial. This in Korean we call this as, right? This is mantan, right? And then what is polynomial? And this means A plus B x plus C x blah 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 blah, and whatever that is, let's say this one is just Z x and maybe n. This is nth order polynomial. Okay, and this, when we have up to here, then we have second order polynomial, and this is actually first order. Order in here means in here we had just one as the highest power. Okay, in here we have 2, the second order. Okay, and this is nth order. In other words, this we chose the linear line because this is the simplest. Okay, and to represent those data, it is also possible that we can have this kind of line, right? Or we can have this kind of line. They can be different form. In this case, if we use A plus bx plus cx squared, then this must be the form of the equation, right? And the only reason we chose this one. It was the simplest or easiest for us to use, right? And also, we only need two parameters if we need to calculate those. In this case, we need three. If we use longer equation, then we need more to calculate. But there are some statistical how do I say it? Statistical. I cannot recall the good word in here. Statistical, or maybe myth, error, misleading, maybe. Statistics is not always right. Statistics gives you some kind of number that sometimes that you want. Okay? And let's say, for example, you have X and Y. You have two data, only two data. And if you have this kind of line, Y equals A2 plus BX. In this case, your line is perfect because you have two data, and if you draw a line, and there is no way for us to have big error because here exact match, exact match. But what if? But we don't really know if we really have more than more than two data, and it is also possible that we can have some values like here. Then this is much is error. Then this is no more perfect line. But in this case, if you use second order polynomial, it is also possible that you can have exact match. But so this one is the function of what? Number of data that I have. If I will have only two data and I can have perfect line, but I don't know if that line is the perfect equation for the situation. So in other words, to have some this statistical approach is meaningful, we need to have enough number of data, right? If you have just limited number of data, then you can mislead. You can go somewhere really wrong. Okay? Alright. So we did it, and then let's define some terms. Let's say our SR is the summation of errors between my observation Y and calculated Y, right? So that SR summation of Y. I don't have enough space. Let me just write in this space. SR equals Y observed. Okay? And Y calculated. In other words, this one is A plus BXI, right? Okay? So this whole thing right here, xi is my independent variable, but A plus BXI right here is the value that I calculated Y based on my information about A, B, and xi, right? So this is that. And another term in here is a summation of Y observed right? And this one is very similar to variance. Okay, this is average. Okay, if you add all up and divide by number of the observations, that's average, mean. Okay, and we call this as standard deviation. The square of standard deviation that we call as a variance. Okay, and if you define by R like this, this is ST right here, ST right there, and then if you define R like that, and since we know everything there, and we can rearrange my R like that. So, and that is usually R is called as correlation coefficient. Right? If this is it 1, and that means we have perfect match. Okay? In other words, if this is 1, that means I have a 0 SR. That means my A plus BXI is exactly the same as YI, so I have 0 for here. Then if I divide same thing, if I have a same thing in the denominator, numerator, and then I have a 1. Okay? But obviously, I always have some error, so I will have some value. So if I have more error, then I have a bigger value here. Then my R, value of R becomes smaller and smaller and smaller. Okay? And also, and often we use R square as a coefficient of determination. So this R value or R scale value is used very often, so that you can say if that line or curve is good for your experimental data. Okay? So this one is good for any type of equation. In here I use only linear line, but I can use A plus BXI plus CX squared, and I can use the longer one. Also, I can use any exponential function, sine, cosine, whatever, if that is your choice of equation. Okay? So very important. And method initial rate, I think I can skip this one. But let me go over the method of half-lives. And half-life is used very often when we are dealing with the radioactive material. I think we cannot just away from the radioactive material anyway. Right? Because when we have earthquake, we worry about that power plant, nuclear power plant, and they have radioactive material. And they produce kind of some X-rays and gamma and alpha, something like that. Some kind of energy that we cannot really see. This kind of X-ray that can be used to picture your inside structure, right? And I have broken my bones 16 times so far. So I got a lot of X-rays. Mostly for sport. Anyway, and this one is kind of the energy, the kinds of energy, and then dependent on their kind of frequency or strength like that. But we want to find out their strength, okay? And this is the kind of concentration. And the half-life means it's a time that a concentration becomes exactly half of original concentration. Okay. So in this case, we can back calculate my t by using integrations. Let's grab a little paper and pen, everyone, and try to solve this equation so that you can come up with this answer. So, what do we need to do? And in here, I need to separate the variable. In other words, if I have x, every x is there, y, every y there, so that I can separate and then and collect by collecting the similar terms in each side. So in this case, I can have a c minus n dc equals k dt, and maybe in here k is constant, and I can just integrate only 1 dt, right? Okay. So then we will just integrate this from c0 plus to ct, and from 0 to t. So then in this case, it's very easy for us to integrate 1, which will be just t, and then we'll just insert t and 0, and insert c0 and ct, and then we can come up with this equation. Okay? Do it now, and I want to see.